Quark-Gluon Plasma stars and their mysterious effects. Presented by William Cochran, an unqualified amateur astrophysicist. Critical energy density, epsilon-c. Epsilon-c represents the energy density at which matter transitions to a QGP-like state during core collapse. This transition can be described mathematically as epsilon-c equals F, m, r, t, EOS, where epsilon-c is the critical energy density, m represents the mass of the collapsing core, r represents the core radius, t represents the core temperature. EOS is the equation of state describing matter under extreme conditions. The function f incorporates these variables and their interactions to determine epsilon-c for a given astrophysical scenario. Gravitational effects. The strong gravitational effects near QGP-stars and their impact on spacetime curvature can be expressed using Einstein's field equations of general relativity. These equations describe the relationship between the curvature of spacetime, described by the metric tensor g, and the distribution of mass and energy. G mu nu equals 8 pi gt mu nu, where g mu nu represents the Einstein tensor, which encodes the curvature of spacetime. T mu nu represents the energy momentum tensor, describing the distribution of mass and energy in the region. Solving these equations for a QGP star system would provide the mathematical description of the spacetime curvature and gravitational effects. Observable properties. Observable properties of QGP stars, such as gravitational lensing and matter accretion, can be mathematically described using equations related to the behavior of light in curved spacetime, gravitational lensing equations, and the dynamics of matter in a gravitational field, accretion equations. These equations would involve parameters specific to the QGP star system and the surrounding environment. It's important to note that these simplified representations do not capture the full complexity of QGP stars and their formation, but provide a starting point for mathematical descriptions of some aspects of the concept. The actual mathematical modeling of QGP stars requires highly advanced astrophysical simulations and a deep understanding of general relativity, nuclear physics, and quantum chromodynamics.